Another really successful method is transits, or transit detection, which relies on photometry and essentially monitoring a star and looking for periodic dips. These dips will be really, really small. They're typically less than 1%, but the importance of these dips is that depending on the size of the dip, we can actually infer the size of the planet. That is because the area of the planet is essentially given by the fraction of your flux lost times the area of the star. And we've seen in section 8 and even before how we can actually use our knowledge of black bodies to determine the size of a star. And therefore, we can very easily determine what is the area of a star. And finally, once we determine this area of the planet, we can very easily measure its radius. We've known about transits for a long time, and we've seen them from Earth, such as the Venus transit or Mercury transit. We've covered how Venus transit is also even fundamental to establish some of the first steps of the distance ladder. But what we're talking about is something we can't really photograph like this, and therefore we can only infer. We're really only looking at flux or magnitude and then looking at changes in that flux or magnitude. We cannot see the actual planet going in front of the star. There are, of course, some limitations to the transit technique. It will only work for edge-on orbits, and that is because if you have a star named Lancaster University, you will only be able to see a transit if it passes directly in front of it. If it's orbiting with an inclined orbit, then this will not be possible. On top of that, this technique does favor very large planets, so it's easier to notice the dip, but also close orbiting planets, because those, even if they are on inclined orbits, they will still pass in front of the star. But one of the huge advantages is the fact that we can use this method to survey really large number of stars at once. And all we need to do is essentially go back to section 7, how we can convert counts into magnitudes, for example, and then look at how the magnitude of a star may be varying just a tiny little bit every now and then. And if there's a certain period, we can actually try to infer the presence of a planet or more planets and also their sizes. As a specific example, let's consider this data right here. And let's say that this team of astronomers were able to find a dip. That's a 1.5% dip. This is quite a big one for an extrasolar planet. And that this was done in the B band. So we're talking about the B band flux of an A3 class star. Now this star, astronomers have actually measured, and you'd be able to do this as well, that the luminosity is 10.5 in solar units, and its surface temperature is 8,750 Kelvin. Apart from measuring this dip, astronomers have also measured that the dip repeats every 3.5 days. Based on what we know, we can actually determine both the radius of the planet and the average separation from the star. The first step is we need to know what is the mass of the star, because we're given the luminosity, and we've seen in section 8 how mass and luminosity are related. We can very easily use that in terms of solar units. And for this specific star, we would calculate that the mass of the star is 1.8. As we now have the mass of the star, and also we have the period, which is 3.5 days, which we need to convert to seconds, of course, if we want to use the international system. This allows us to calculate what is the average separation between the star and the planet. And we can actually find a value that may ring a bell because we just calculate something very similar, 0.055 AU. The reason why this value is so similar is because we're actually looking at the same system. This is the same planet and star, and we'll see that we can actually combine data. But for now, we still need to try to determine the radius of the planets. We already calculated the separation, but we need to calculate how big the planet is. In order to do that, and because our measurement is relative to the flux of the star, so we're talking about 1.5% to the star, we need to calculate how big the star is. And we've seen that we can use our knowledge of black bodies, and specifically in section 8, we explored how we can do this and calculate the size of a star based on its temperature and luminosity. For this A3 star, we actually know both quantities, and therefore we can calculate that the radius of the star is about 9.9 times 10 to the 9 meters. Given the fraction of flux lost, we can actually calculate that the area of the planet is essentially the fraction of the flux lost times the area of the star. This gives you this value. And finally, you can actually calculate the radius of the planet by just getting the square root of the area of the planet divided by pi. And ultimately, if you divide by the radius of Jupiter, you can find out that this planet actually has a radius that's 17.3 times the radius of Jupiter. And therefore, it is a really, really big planet. The transit method is really powerful. It allows us to monitor many, many stars at the same time. And in principle, if our accuracy is really good, we can even detect Earth-like systems with periods of about 1 year. However, there are important limitations to be aware of. One of them is the fact that using the transit method in things like star clusters is extremely challenging, just because stars are passing in front of each other all the time, and therefore we cannot really assume that whatever caused the dip was a planet, because very likely it was another star. But perhaps even more important is to understand that stars, pretty much like the sun, they can actually have changes in flux with a given period. We actually talked about this in section 10. We looked at how the sun can actually develop sunspots and how they actually have a cycle of about 11 years. And for the transit method, because all we're doing is monitoring the flux, if we were observing the sun from a really large distance, then we would actually be able to see that the sun's flux would go down every 11 years, and we could actually try to infer what kind of planet is causing that. But there is no planet with a period of 11 years. That's just the solar cycle. And of course, many other stars will have this activity and variation, and therefore, many of the claimed planets so far discovered through the transit method were actually then shown to be stellar activity and not real planets. And this is one of the big reasons why whenever we discover planets with a transit method, we typically would want to confirm them with radial velocity so that we are sure that there is an actual mass causing that, and it's not just the activity of the star itself. If it's the activity of the star itself, then we'll see no movement of the star with the same period. But if the movement of the star matches the period that we infer from a transit, then we know for sure that it has to be a planet. Another reason why we would want to have planets confirmed with both the Doppler and the transit method is because we can actually combine the information to learn even more. The transits method will tell us about the size of the planet, while the Doppler effect, or radial velocities, will tell us about the mass of the planet. What this means is that if we combine both, we can actually determine what is the density of the planet and therefore infer something about its composition. Another thing that we can actually tell about a system, if we can detect it both through transit and Doppler, is the fact that its inclination is probably around an eye angle of 90 degrees. This is the only way you can really see transits. If we do that, then we can actually use the system that we've calculated, and we can actually take the sine I dependence and therefore calculate an actual mass. And for that planet, we would conclude that its density would be 1.68 kilogram per cubic meter. If you find something like this, you can probably try to compare it, and surprisingly enough, air on Earth has a density of about 1.2 kilograms per cubic meter, which would imply that this planet is essentially made of air. A planet made of air that is really close to a star is not something you'd actually believe. And this is, of course, a consequence of me just making up these observations and this planet without even considering the density. This is also the reason why extragalactic astrophysicists should never create extrasolar planets.